All right, so this video is going to be going over a series of videos, or the first of the series videos. It's going to be in topology and metric spaces, and this belongs into the Baby Real Analysis YouTube playlist. Again, this is a baby real analysis, so it's at a very elementary level. So first I'll go into what a topological space is, and then I'll go into metric space and the concept of neighborhood and interior point. So here's the definition of a topological space. Note that with the real number line, we are using the metric that's the absolute value. So d for distance is equal to the absolute value of x minus 8, or sorry, x minus y. And this actually gives a topology on R induced by the metric d, where d is the absolute value. So a topological space is more abstract than a metric space. And here is the definition of a topological space. There are three requirements or three properties of a topological space. So you have some set X with a topology tau. That's a commonly used letter that uses tau. And this pair, the set X with tau, is going to be a collection of subsets of X. These subsets are themselves called open sets. So as long as they're in this collection of subsets, then that is an open set. And the three properties, you need to have the set X and the empty set. The second property is arbitrary unions of subsets are in the collection. And then the third requirement is that finite intersections of the subsets are also in the collection. So as long as it meets these three requirements, then you have a topology, and in particular, a topological space on some set X, which is denoted right here, X comma tau. So here's just a very trivial example. Let's say X is some set, and we have tau being defined to be the collection of the empty set and X. And the question is this pair, X with the topology tau, is that a topological space? And to check it, we know that, well, the first requirement is met, because by the definition of tau already has the empty set in X. So first condition is met. Second condition is talking about arbitrary unions of the subsets in the collection are also in the collection. Well, we just there's only two sets in tau, so when you union them, you could do the empty set union with itself, but that's the empty set. And that's in our collection of subsets. So because it's the empty set in X, you could do X union with itself, but that's just X. And that's also in our collection of subsets. Or you can do the empty set union with X. And this is going to be X, which is in our collection of subsets. Because again, it's just tau, it's just the empty set in X. All right, so these are the possible unions you can do. I guess you could, yeah, because there's only two things. So empty set union with itself is the empty set. X union with itself is X. And then anytime you take the union of the empty set with some set, let's say set X, it's going to be that set X. All right, so the second condition is met. The third condition, sorry about that, third condition is talking about finite intersections of the subsets. There's only two subsets, so any intersection I'm going to do is finite. So if I take tau intersected with itself, sorry, not tau, the empty set intersected with itself. That's just the empty set. If I do x intersected with itself, well, that's just x. And again, these are in tau. And then if I do the empty set intersected with x, well, that's going to be the empty set, which is in our collection. And those are the finite intersections you can do. And they produce subsets that are part of our topological space, or our topology tau. So all three conditions are met, and so therefore this is a topological space, yes. And I believe this is just called the trivial topology. It's not very useful, but this does just give you an example of showing how a topology creates a topological space by meeting these three requirements. And I want to stress that the subsets of that topology are themselves referred to as open sets. Okay, so just a couple more examples of topologies, checking that it's a topological space. Say you have X consisting of the members 1, 2, and 3, and let's take tau to be the collection of the empty set X and the subset 2. Now, is this a topological space? Well, condition 1 is met because we have the empty set in X. Now, if we take arbitrary unions of the subsets of tau, are they also subsets of tau? Or in other words, are they also part of the collection that tau is? And what I've done here is listed out different unions. So like the empty set union with the empty set is the empty set union with X is X. The empty set union with the subset 2 is just the set 2. Again, anytime you take the empty set union with another set, as long as that set's not the empty set, well, I guess if it is the empty set, it is the empty set, but empty set union with a non-empty set is just going to give you that non-empty set. All right, so then I have X union X, which is X, X union 2, which is X. Okay, we're taking the union here. 2 union 2 is the set 2. And then I could take the union of all of the elements. So X union the empty set, union 2, and that's going to give me X. And so all of these produce subsets that are part of a collection of subsets. Again, these are just some trivial, or not, I guess, I know they use trivial too much in math, but these are just some simple examples of, just to go through the concept of topology. And then we'll be going into metric space. Now I need to check that condition 3, our finite intersections, are they going to be subsets of our collection of sets? So what I've done here is take different intersections. And I know when I intersect the empty set with any set, it's going to be the empty set. So that's what I wrote here. So if I take the empty set and intersect it with all of these subsets, they're going to be the empty set, which is part of our collection. Like the empty set intersect with X is the empty set. The empty set intersect with the subset 2 is the subset 2. And these are going to be all part of our collection of subsets. Then if I did X intersected with the different sets, again, these different sets are just X2 and the empty set, but we just already took care of that one. When you intersect X with the empty set, that's going to be the empty set. All right, now if I intersect X with itself, that's X. If I intersect X with the subset 2, that's going to be 2. Again, X is consisting of the numbers 1, 2, and 3. And so the intersection of the two sets, being X and 2, would be just the set 2. Then I can take the intersection of 2 with itself. Again, that's just going to produce the set 2, part of our collection. And I could do the intersection of all 3 And anytime I intersect with the empty set, that's going to give me the empty set. I could also do an intersection of X with itself with 2, and then that's going to produce 2. And so what I've kind of wrote here is that, so I might not have listed every single intersection, but the point is that if you intersect all elements or all subsets, it will result in the smallest subset they share. Whereas if you union all elements or all the subsets, the union's going to be, and I'm putting in quotes, biggest subset they share. I hope that makes sense. I'm very usefully using the word smallest and biggest. All right, so this is a topological space. Now here is an example. I'm not going to go through all the criteria, but this does form a topological space. So if you have some set X within elements, the power set, which I denote this curly looking P, so this is the power set of X. And the power set of X, as long as X is in elements, is going to have 2 to the n elements. The power set is all subsets of X. And that will include the empty set and X itself. So here, let's say I have X as one, the set just 1 and 2. The power set would be this, X, the set 1, the set 2, and the empty set. And you can check the 3 properties, and you'll see that it meets the 3 properties, and so it's going to form a topological space. So the power set is like a topology on X. So this would be a topological space. Again, this is very abstract. So this is just going into first topology, giving a brief preview of topology. And what I'm going to go into now is metric space. So note that the topological space is more abstract than a metric space, in my opinion. And the elements of the topological space are by assumption open sets. All right, so by assumption of being part of this collection of subsets, tau, then they are an open set. Now, metric space is a type of space that can give rise to a topological space where open sets are determined by some metric that forms a neighborhood. So some metric, and you have this terminology called neighborhood. Here are the requirements for a metric space. So you consider some set X, and you have a function using X cross X into the real numbers. Really, it should have been more restricted. It's going to be the real numbers greater than or equal to 0. All right, so really should have been R, real numbers that are greater than or equal to 0. This forms a metric space as long as you have these 4 things. So if I apply this function d between 2 points, any 2 points x and y that are part of the set X, so if I apply that function, then d of xy is going to be greater than or equal to 0. And this is called positivity. Now apply the function d, and then your 2 elements is x and x, then that's going to equal 0 if and only if x equals x, and that's definiteness. So we'd like the notion of distance to produce some distance between 2 points should be positive if they're 2 distinct points, and then the distance between 2 points should be 0 if they're the same point. Okay, that's basically what that's saying. We'd also want symmetry, like the distance from x to y should be equal to the distance from y to x. And then here is the triangle inequality. And so I just put a triangle and then inequality. So if you have 3 points, x, y, and z, and you take the distance between x and z, that should be less than or equal to the distance from x to y plus the distance from y to z. So as long as it has these things, then x comma d forms a metric space. In the baby real analysis playlist, we've been dealing with our distance being absolute value. All right, so that's what we're going to usually do for most of these videos in this particular part of the playlist is using absolute value. But we don't have to, we could use different distances. All right, so the real numbers paired with this d, in particular distance d using absolute value is a metric space. You can check that it meets all those requirements by using the definition of absolute value and all those properties of absolute value that are in the beginning, near the beginning of the playlist for the behavioral analysis playlist. All right, so next thing I want to discuss is neighborhoods in this metric space. So the neighborhood I'm referring to is kind of like the neighborhood that's used in Rudin's text. Again, the texts are principles of mathematical analysis for Rudin. I use Bartol's introduction to real analysis, and then also Cummings' real analysis, a long form textbook. I've been mainly using the other two. Now with these playlists, this part of the playlist, I'm going to be using a lot of Rudin's terminology. Okay, so neighborhoods in RD. So this is the notation I'm going to use for an epsilon neighborhood of P. And so it's going to be the set of X such that the distance from P to X is less than some epsilon. And again, epsilon is going to be some number bigger than 0. And I'm going to call that an epsilon neighborhood of point P. So a lot of the times, instead of writing neighborhood, I'm going to abbreviate it as nbhd. So again, we've been using the distance function in the reals to be the absolute value between 2 points, the difference, absolute value of the difference between 2 points. And so an epsilon neighborhood of some point P would be to set X such that the absolute value of X minus P is less than epsilon. So what I did here was translate what this means. And this is just properties of absolute value with inequalities. And so I would say see beginning of the playlist for more details. I actually do talk about a neighborhood in the near the, I guess, first 10 videos of this playlist. All right, so we have this epsilon neighborhood, and it's defined to be the set X of all the points X such that the distance between X and P is less than epsilon, where our distance is going to be the absolute value. All right, so here I have absolute value of X minus P less than epsilon. That'll translate into this, negative epsilon less than X minus P less than epsilon. And then I can rewrite it by adding P, and then I'll have P minus epsilon less than X less than P plus epsilon. And so this forms an interval, open interval. X is a member of the open interval P minus epsilon, so P plus epsilon as your left endpoint and right endpoint. Again, these are open parentheses here. So that means to not include those. So I just drew a real number line, and I drew the interval P minus epsilon comma P plus epsilon, and your point P is considered the center point of the neighborhood. And X ranges in between the endpoints P minus epsilon, P plus epsilon. And P would be like considered our center point. And a lot of the times I'll write the word point as PT. All right, so that's just some terminology. This is what an epsilon neighborhood is in terms of the distance metric d. And then if we're using absolute value, the epsilon neighborhood is this, which can be translated into this open interval. All right, so here's an example where I'd put an epsilon neighborhood around the point 0. So this is just, I just drew some open interval. Again, this is on the real number line. And so we have epsilon being the right endpoint because we want to use, it's like consider P, our center point, being 0. And so P plus epsilon would be 0 plus epsilon, which is epsilon. And then our left endpoint, that is our P minus epsilon. Well, that's 0 minus epsilon, which is minus epsilon. And so this is just an epsilon neighborhood around the center point 0 on the real number line. And again, I'm by assumption using the distance or metric being the absolute value between 2 points. Okay, so that's neighborhood. Now I want to talk about interior points. So we can consider the metric space R with the metric D, and E is a subset of R. X is a member of E, is an interior point of E, if there exists an epsilon such that the epsilon neighborhood of X is contained in E. So this is what it means to be an interior point. Here I go through just an example. So given the open interval 0 to 1, subset of the reals, and the distance being the absolute value, I'm going to check that 1/2 is an interior point of the open interval 0 to 1. All right, so as long as I produce an epsilon, because it just says there exists an epsilon, then I can make that epsilon neighborhood to be contained in that 0, 1. So what I need is to produce some epsilon bigger than 0, such that the epsilon neighborhood around my center point that we're checking here is, we're checking if 1/2 is an interior point. So I use 1/2 as my center point. And so we need to see that that is contained in 0 to 1. Well, here I could pick epsilon to be 1/3. That's a number bigger than 0. And the 1/3 neighborhood about 1/2. So this is taking 1/2. So again, it's kind of like my P minus epsilon to be like my center point P plus epsilon. So I'm just using 1/2 minus a third and 1/2 plus a third. Well, that's 1/6, 5/6. So the 1/3, 1/3 neighborhood about 1/2 is this open interval 1/6 to 5/6, and that's entirely contained in 0 to 1. So therefore 1/2 is an interior point. I could have used a different value than a third. So for the specific example of 0, 1, epsilon being 1/3 is just one value we can use. In fact, I can use any value epsilon as long as epsilon is between 0 and 1/2. 1/2 being the biggest. Okay, because we're dealing with not including the endpoints anyways. So the biggest open interval subset of 0 to 1 is 0 to 1. And that would be when I use 1/2 for epsilon. All right, so just to go through the motion, let's say if I wanted to check that 1/4 is an interior point of 0 to 1. Drawing the picture isn't necessary, but 1/4, that's somewhere right there. I just need to find some epsilon so that the epsilon neighborhood about 1/4 is contained entirely in 0, 1. So as a picture, I could find some neighborhoods, some be open interval about 1/4, such that that open interval is contained entirely in the, let's say, bigger open interval 0, 1. Okay, so as long as I produce some epsilon, then that's fine. So all I got to do is just pick some epsilon. So let's say I just pick epsilon to be 1/10. I don't know, I just chose something, and I'll show that this works because, again, the epsilon neighborhood about 1/4 would be the interval of 1/4 minus epsilon, 1/4 plus epsilon, and so I'm using 1/10. And then check that that's contained in 0 to 1. Okay. All right, so that means 3/20 is 1/4 minus 1/10, and then 7/20 is 1/4 plus 1/10. And this is contained in 0 to 1. So therefore, 1/4 is an interior point. Again, I just need to find some epsilon that works. Okay. Now, before I go into this, I do want to talk about some extra clarification on the term neighborhood. So the neighborhood, in this case, I'm calling an R neighborhood because I'm using this subscript R here about P in the metric space R equipped with metric D, sometimes referred to as the open ball centered at P with radius R. So this neighborhood I've been dealing with in the previous example is actually called an open ball. All right, so that's some terminology you'll see in different real analysis or, basic analysis classes. You might use the open ball terminology. And so the word open ball and a neighborhood in this metric space is an open ball. Okay, so that's like an open ball is a specific is a type of neighborhood. All right, and again, the R neighborhood about P is going to be the set of X such that the distance between X and P is less than R. And so open balls are the neighborhoods in our metric space R comma D. Now, in general, a topological space, what about a topological space that's not reliant on a metric D? So there's also that question. So you can have a neighborhood in a topological space, but we're not using distance as our definition for the neighborhood. Well, let's say you have X being A, B, and you have tau being the empty set X, A, B, and this is a topological space when I do X comma tau. And again, the members of tau are considered by assumption open sets. Sorry. So by assumption, the elements are considered open sets if they belong in this collection tau. What would be a neighborhood of, say, let's say the point P equals A, which is part of X? So what would be a neighborhood in that case? So a neighborhood in a topological space say X comma tau instead of using in subscript R, where I had R as the, really, we were using it in terms of open balls, where R is the radius. Instead, I'm going to just write it as in. So a neighborhood, and if you have some point A and X, then I can find there exists a neighborhood in of some point, let's say n of A, such that n of A is a subset of our topology, of our topological space. Okay, so again, X is just A and B. Tau was basically all the subsets of X. So we have the empty set X, and then the singleton sets A, and singleton set B. I just need to find some set about A that's contained in the topology. Well, I can use my neighborhood to just be the set singleton set A itself. And the singleton set A is a member of tau. And so this is considered a neighborhood of just a topology. All right, so a neighborhood is just a subset that's in the set collection of sets, tau. So that's what it means in terms of just topological space. I just wanted to clarify that there is a difference between neighborhood and open ball. But with this course, I'm just using neighborhoods in terms of basically as open balls. But I'm just using the word neighborhood to be consistent with Rudin. All right, I hope that makes sense. I think the next video I'll go into this, open sets in the metric space, and talk about what it means to be open, and go through some simple examples of showing that, in this case, this open parentheses set 0 to 1 is going to be open in the metric space R to D. And then another one, just in broad terms, is A to B being any two real numbers. So I'll talk about what it means to be open in a metric space in the next video.